Hello, everyone, and welcome back. We are picking up with Chapter 4, Stoichiometry of Chemical Reactions. Now, couple notes for this chapter. We are spending 2 weeks on it. So, this week we are only going through sections 1 and 2 of Chapter 4, and next week will be sections 3, 4, and 5. And section 2 is also going to be two separate videos because it's a very dense chapter with a lot of information, and I do not want to overload you guys. This chapter is probably the most important chapter of this book and of this class, as it's the foundation for chemistry. It's all about chemical reactions, being able to balance them and interpret them and identify types of reactions, which eventually you can use for predicting what the products of a reaction can be. So that being said, let's get started with section 4.1. Just a quick outline, 4.1 and 4.2, what we're going over this week, are writing and balancing chemical equations and classifying chemical reactions. Next week's videos will be on reaction stoichiometry, reaction yield, and quantitative chemical analysis. So we're starting with 4.1 and just giving you a quick intro picture to pique your interest. Rocket fuels are actually solid mixtures, and you had actually a question in last week's homework for ammonium perchlorate, which is used as solid rocket fuel. And we're going to look at that reaction actually a little later. So in 4.1, we are going to be deriving chemical equations from narrative descriptions of chemical reactions, and writing and balancing chemical equations in molecular, total ionic, and net ionic formats. So it's really important that you are able to interpret a chemical reaction that is written in words. So if you're given the name of a compound, you need to be able to write its formula. And we're going to talk all about that. So chapter 3 is very important. It goes along with chapter 4. And that also does bring me to another point. Chapter 4 is the end point for midterm 1. So after next week, our first midterm is in 2 weeks. Not next week, the week after. So I hope you are preparing. Okay, so let's get into this. In the chapters we've studied so far, we've talked about using symbols to represent atoms, molecules, and compounds. So chapter 3 was all about molecular and ionic compounds, how to write their formulas, calculate their molar masses, and do calculations involving moles and molarity and all that fun stuff. So in this chapter, we're going to start by looking at balanced chemical equations, which use symbolism to represent both the identities and relative quantities of substances that are undergoing a chemical or occasionally a physical change. Kind of funny how wordy that description is, based on symbols. All right, so figure 4.2 here gives us an example of a chemical equation and the reaction that it's representing. So to start, every reaction has 3 parts to it. The first part I want to point out is this center arrow that goes from left to right. To the left of the arrow, you have the reactants. These are what are reacting. Okay, so this is what we're starting with. You can also kind of think of the arrow as an equal sign for my math-minded people. On the right side of the arrow, we have the products. So these are what are produced or made when our reactants combine. If you have more than one reactant or product, they are separated with plus signs. Okay, so here we're saying CH4 plus 2 O2s combine to form, or reacts to form is a way to say for this arrow, CO2 and plus or and 2 waters. Whoops. And then to show kind of what they're what they stand for, CH4, we have some molecules here. So we have one of this methane or CH4 molecule with 2. So these coefficients that might be in front of a formula tell you how many of a particular molecule there may be. So we have two O2. So we have two oxygen molecules. There's 1 and 2. So these combine to form 1 carbon dioxide and 2 water molecules. If there is no coefficient in front of a formula, that just means 1. So what I used to do is I would kind of draw 1. I would put in a 1 with little dashed marks just so I knew that I meant 1. So again, the substances that are undergoing the reaction that are on the left side of the chemical equation are our reactants. The ones on the right are the products. We use plus signs to separate the different compounds. The arrow separates the reactant and product side. And we use coefficients to give us the relative number of reactant and product species. Now, kind of like with the chemical formula, we want to use the smallest possible whole number coefficients in a chemical equation when we are making sure it's balanced. And we'll talk about what a balanced equation is in just a minute. But what these coefficients represent is the relative numbers of reactants and products. So the ratios, okay? For instance, in the methane, CH4 plus 2O2 becomes CO2 plus 2H2O. We're saying that we need 1 methane to react with 2 oxygens to form 1 carbon dioxide and 2 waters. I'm not sure if you heard that meowing, but that's my foster kitten, Charlie. He's getting fed right now by my mom. Being a little fussy. Nonetheless, this shows us our ratios. You can interpret these numbers as molecules. You could say I need 1 methane molecule for every 2 oxygen molecules. You can even use this as moles, and we'll talk way more about that next week. So it doesn't matter what the actual number of molecules are, the ratios are the same as what's given in the equation. So this equation we've been looking at is called balanced. It's a balanced equation. And what that tells us is that on each side of the arrow are equal numbers of atoms. So looking at it again, I'm going to write it again. CH4 plus 2O2 becomes CO2 plus 2H2O. So we can make a little table. And I'll show you the one that I make, and then I'll show you theirs. It's basically the same thing. But I put a little R for reactants, a P for products. Chemists are lazy. I'm not going to write the whole thing out. I know what it means for R and P. And then I'm going to go and list each of the atoms that are in my formula. So I have C for carbon, H for hydrogen, and O for oxygen. So what I'm going to do is I'm going to look on starting with the reactant side and write down how many of each atom I have. So I have 1 carbon on the reactant side. I have 4 hydrogen, so that 4 represents 4 hydrogen. That's why it's only on the H. And then I have 2 O2s, which means I have a total of 4 oxygens. On my product side, I have 1 carbon. And then my oxygens, I have 2 in the CO2. And then 2 waters means I have 2 oxygens. So that's a total of 4 oxygens. And then I have 2 times 2 hydrogens, 4 hydrogens. So notice everything is balanced on both sides of the equation. And we are balanced. Oh, Charlie. So like I was just showing, sometimes an element might be on a side of the equation in more than one place. And you just still add up all the atoms. Don't let it scare you. So your book does basically the same thing I do with the table. Theirs is a little bit more involved. They show their math here. It's whatever works for you is perfectly fine. Okay, So sometimes a lot of times you'll be given a reaction that is not balanced. For instance, we're given H2O becomes H2 and O2. So if we look at this, we notice on the reactant side, I have 2 hydrogen and 1 oxygen. On the product side, I have 2 hydrogen and 2 oxygen. So even though our hydrogens are balanced, our oxygens are not. So we need to add coefficients to some of these different parts of the equation to balance it. So the coefficients, the numbers in front of your molecules, okay? You cannot change subscripts. Do not change subscripts. Okay, you can't go and change H2 to H4 because why? No, that doesn't work. Only the coefficients. So to balance the oxygen, we notice that there's more oxygens on the product side than the reactant side. So we're going to go ahead and say, okay, I want to get 2 oxygens. So I'm going to start by putting a 2 in front of the H2O, in front of water. And when I do that, now I put this 2 across to the parts of water, and I see now I have 4 hydrogen and 2 oxygen. So now my oxygens are balanced. I have 2 on each side, but my hydrogens are not. I have 4 on the left and 2 on the right. So now to balance my hydrogens, we can add a coefficient there. We can put a 2 in front of that H2 on the product side, and now everything balances out. I have 4 hydrogens on each side and 2 oxygens on each side. So now it's nice and balanced. So here's another example, and I wanted to go through this one in particular because it has our old friends, the polyatomic ions, in it. So when it comes to balancing an equation with polyatomics, unless you don't see them on both sides of the equation, don't break them apart. So for instance, here we see NO3 and CrO4. These are both polyatomic ions. So when we make our little table, our reactants and our products, instead of breaking them apart into their relative atoms, I mean, you can do that, but it's going to make life an absolute pain for you. We're going to say instead we have silver, we have potassium, we have NO3 nitrate, and chromate, CrO4. So, looking at both sides, I have, starting with the reactants, I have 1 silver, I have 2 potassium, 1 nitrate, and 1 chromate. So notice there's no parentheses around the polyatomics here, and no subscript. So if there was a parenthesis and a subscript, around the NO3, then maybe you'd have 2 NO3. But not here. On the product side, we have 2 silvers, we have 1 potassium, 1 nitrate, and 1 chromate. So definitely not balanced here. So it really doesn't matter what we decide to balance first. So I say let's balance silver first. So I'm going to go ahead and put a 2 in front of AgNO3. Because that's where I have the lower number. So now that changes my reactant amount of silver to 2, and my reactant amount of nitrate also to 2. Because now there's 2 NO3s as well. So now we notice that our CrO4 and our nitrate are not balanced. So I say let's go ahead and do nitrate, the NO3. So we would have to put a 2 in front of KNO3. And now that changes our potassium on the product side to 2, and our nitrates on the product side to 2. And look at that. Sorry, I misspoke. Our chromate is already balanced, 1 on each side, 2 nitrates on each side, 2 potassiums, and 2 silvers on each side. We are balanced. Yay! So sometimes it can be helpful to use fractions instead of integers for intermediate coefficients. So they're not going to stay like that. For example, in this reaction shown here, C2H6 plus 7 halves O2 becomes 3H2O plus CO2. So this started off pre-balancing as C2H6 plus O2 becomes 3H2O plus CO2. And the numbers are kind of a pain here. So if we look at our reactants and our products, we have carbon, hydrogen, and oxygen. 2 carbon to start, 6 hydrogen, 2 oxygen. On the product side, oops, that shouldn't say 3 water, that should just say water. On the product side, we have 1 carbon, we have 2 hydrogen, and 3 oxygen. Oh, excuse me. So, if we decide we're going to balance our hydrogen first, we need to put a 3 in front of the water. Okay, and that gives us 6 hydrogen on the product side. And now our oxygen on the product side has turned to 5. Kind of a weird number, right? 3 waters. Yeah. So now we're kind of in a pickle. We're like, okay, how am I going to balance this, right? We can go ahead and put a 2, though, in front of the CO2 to balance that out. And now that gives me 2 carbons on the product side. So now we have 2 on each side. And 7 oxygen on the product side. So figuring out like a common number to fix things is a pain in the ass. Pardon my French. But it's true, right? However, if instead I put 7 over 2 in front of oxygen, 7 halves times 2 equals 7, which would give me 7 oxygen on each side. See that? So it's balanced. But we don't like half numbers in our equation. So every single coefficient, we're going to multiply by 2 to get rid of that denominator. So then that is going to make this 2 C2H6 plus 7 O2 becomes 6 waters and 4 CO2s. This is balanced. We don't have a fraction. Everything is happy. But when you have to mess with big numbers like this, sometimes it can get really annoying trying to figure out what to change and how to change it. So this is a way you can do that. You can go ahead and use like a half, use a fraction very quickly, and then you get rid of it. Now, chemical equations can have some other information in them. One of the first things are the physical states, and we've seen most of these before. G, in parentheses, means gas. L means liquid. A lot of times when I write, I do a little cursive L. It's just habit, something I was taught by my chemistry professors, and I just never stopped. S for solid, and AQ for aqueous. Remember that means dissolved in water. Occasionally, you'll also see little symbols above an equation's arrow, or sometimes even words. So for instance, if you see a little triangle above the arrow, that means delta, which means heat. So it's the Greek letter delta, and when that's over an arrow, that means heat is needed for a reaction. That's just an example. Sometimes you'll see different things that indicate catalysts and other things above the arrows. All right, so let's talk about some ionic reactions in water. So a lot of chemical reactions take place in aqueous media, aka in water. In chemistry labs, a lot of times you're using solutions with different molarities and combining them. So when this happens, ionic compounds, hence the term ion and ionic, can dissociate or break apart into their relative ions. And we're going to look into that. Now, molecular compounds don't do this. They stay as themselves, but ionic compounds are a little different. But let's go ahead and first look at this equation given here. We're told aqueous calcium chloride is reacting with aqueous silver nitrate to form aqueous calcium nitrate and solid silver chloride. This doesn't actually tell us much of what's going on. This is its molecular equation. So this is the overall equation. Everything, the compounds are still together in their formulas. Okay. But this doesn't really tell us what's going on for the ion species. Because in reality, ionic compounds can dissociate into the ions that make them up. For instance, if you stick calcium chloride in water, it splits apart into calcium 2+. Remember, it's in group 2, so it has that 2+ charge. And 2 Cl minuses. Okay, because you have Cl2 here. It doesn't stay around as Cl2s floating in water. Chlorine, when it's the chloride ion, is Cl minus. Since you have 2 in the formula, that means you have 2 Cl minuses. Silver nitrate, we're told it's aqueous, and we look at it, we notice this is ionic because you've got a metal bonded to a polyatomic ion. That's our nonmetal. So that's going to break apart. And then we have to, because silver may have different charges, we need to make sure that we have the charge right here, because silver isn't one of our main group ions. So nitrate always has a charge of -1. It's a 1-to-1 ratio, so silver here is also -1, or +1, sorry. And there's a 2, since the balanced molecular equation has a 2 in front of it. So that means I have 2 silver ions and 2 nitrate ions. And then calcium nitrate breaks apart into Ca2+ and 2 NO3 minuses. Notice AgCl is not listed here because in the equation, we're told it's a solid. Okay, so solid compounds, if it's a solid ionic compound, it does not dissociate. It does not break apart. So that's this type of reaction. We'll talk more about it in the next section, but this is a precipitation reaction. So you put 2 aqueous solutions together and you make a solid. It's really cool. So we can go from that molecular equation to a complete ionic equation. And so what we're doing is we're rewriting everything that makes up that equation and dissociates into the ions. We're now writing them as ions in our equation. So calcium chloride becomes Ca2+ plus 2 Cl minus. So we've got this big long guy here. This is the complete ionic equation. This is all the ions plus our silver chloride here that's filling as a solid. Now, one thing you might notice is there's some ions that are on both sides of the equation. Let's talk about these. So you should notice that calcium 2+ and NO3 minus, you have the same numbers and they're the exact same on both sides. If this were a mathematical equation, okay, we could say we have x plus 2y plus 2z plus, didn't think about this right, 2a is equal to, and calcium 2+ is represented by an x plus 2y, nitrate is 2a, so 2 nitrates, so I have 2 a's, and this AgCl is b, whatever. So if we were to look at this as a mathematical equation, we'd say, hey, look, x and 2a, we have those on both sides of the equation. Those cancel out. They subtract out to be 0. Same thing here. So the calcium and the nitrate cancel each other out. And we're left now with the net ionic equation, which is Ag+ plus Cl minus becoming AgCl. This is the whole reaction that's happening. All the other ions are doing nothing. They're just floating around. They're called spectator ions, or what I like to refer to them as are Raider fans. Sorry, I gotta go after Raider fans. No offense, sorry, not sorry though. Or whatever team you may not like if you're a sports fan. If you're not a sports fan, I don't know. Something that you watch. So the reason that I compare it to that is most of us have watched some type of sporting event, whether it's on our couch, especially right now with quarantine, or in a stadium. And I can pretty much assume all of us, even if we don't say it out loud, has had some things to say to the teams, to the refs, to whoever. We might be sitting there going, well, that was a bad call. Why would you do that play? That was clearly a strike. That there was a foul on the play, whatever it may be. In reality, no matter how much we yell and scream at the team, are we making a difference? No, we're spectators. We're just chilling. Well, some of us have no chill, but you know what I mean. Same thing with spectator ions. Okay, they're there. They keep everything charged neutral, but they're not changed. They don't actually react. There's no chemical, there's no physical change. They're just chilling, staying dissolved in water and not changing. So the actual reaction that's happening is this silver plus ion is combining with the chlorine minus ion to form silver chloride. All right, so let's look at an example. We're told carbon dioxide is being dissolved in an aqueous solution of sodium hydroxide to make an aqueous solution of sodium carbonate and liquid water. And we want to write the balanced molecular, complete ionic, and net ionic equations for this process. So the first thing we need to do is write our equation. So we're told carbon dioxide and that's a gas, or aqueous carbon dioxide, sorry, dissolved in an aqueous solution of sodium hydroxide. So it's combining with sodium hydroxide, and it is forming sodium carbonate. So carbonate is CO3 2 minus, and sodium is Na plus. So if we do our good old crisscross, this is Na2CO3 plus H2O liquid. So we have our unbalanced molecular formula here. So if we look at this, let's make our chart really quick. Reactants, products, boom, boom. We have carbon, we have oxygen, we have sodium. Notice we do have the polyatomic ion of carbonate here, but it is not on both sides of the equation. It is only on the right side. So let's see, our reactants, we have 1 carbon, 3 oxygen, and hydrogen. We have 1 sodium and 1 hydrogen. On the product side, we have 1 carbon, 4 oxygen, 2 sodium, and 2 hydrogen. So we notice that sodium, hydrogen, and oxygen are not balanced. So if we start by balancing sodium, let's put a 2 in front of NaOH. That changes our reactant sodium to 2 and our reactant hydrogen to 2. And our reactant oxygen now, this is 2 oxygens plus the 2 from CO2, is 4. Hey, look, we balanced it. So now we've done the complete molecular equation. Pretty easy balancing. Nice when it works out like that. I'm going to go ahead and erase my little table here so we can have some room. So now we have our complete molecular equation. So the next thing to do is to go ahead and figure out our dissociation into ions. So we're going to start by looking at our ionic compounds, and they're the ones that are going to break apart. So carbon dioxide is not an ionic compound, so it stays as CO2. But sodium hydroxide is an ionic compound, so it's going to split apart to its cation and anion. So that's going to give us 2 Na pluses, okay, because that 2 coefficient in front of it, and 2 OH minuses. Sodium carbonate is an aqueous ionic compound, so it's going to split apart. And that's going to give us 2 Na+, since I have that subscript 2 on the sodium, plus CO3 2- aqueous, plus H2O liquid. Sorry, I ran out of room there. Okay, water is a liquid. Water is not aqueous. It's not dissolved in itself. Even if it was, it still is not an ionic compound and does not dissociate. So now we have written the complete ionic equation. So there's step 2. And the last thing that we are told to give is the net ionic equation. So let's go ahead and identify any spectator ions we may have. And I look and I see 2 Na+ on both sides. There's my spectator ion. Everything else is unique. So our final equation, our net ionic equation, is CO2 aqueous plus 2OH- aqueous, react to form CO3 2- and H2O liquid. And there we go. And if you were to go through and look at this, you would see that it is completely balanced as well. You have the same number of atoms on each side. Everything's good.